Okay, so we'll continue our exploration of the motion of rigid bodies in 3D by developing Euler's equations of motion of a rigid body. And we're going to start with Newton's second law as applied to rotations, which says that the torque on something is equal to the time derivative of the angular momentum. Now, keep in mind that's evaluated in some fixed frame. Now, there's a complication here, and that's that this can become a computational bear really fast. You're still going to want to go ahead and say that the angular momentum is equal to I dotted with omega typically. Unfortunately, as the object rotates, it means the distribution of mass is going to change in the fixed frame, which means that I is dynamic. That's something that you probably want to avoid if you can help it, and so it's going to make more sense to analyze it in the in a rotating frame, because in a rotating frame, especially if we're clever about our choice of rotation axis, we can keep the moment of inertia constant. Now, this is going to add, we'll have to evaluate the LDT in a rotating frame, and remember, that means that we also have to add in omega cross L. Okay, so that's good. So we've got that L dot in the rotating frame plus omega cross L. So we can go ahead and write that out. Our L dot will be a ddt of I dotted into omega plus omega cross I dotted into omega. Okay. The advantage of evaluating this in the rotating frame like we are is that the moment of inertia tensor is a constant. And so this term just becomes I dotted into omega dot, and we had the penalty that we have to carry our omega cross I dot omega. All right, now since we've already gone to the effort of putting this into a rotating coordinate system, it's going to make some sense to go ahead and choose the principal axes as our coordinate system to make things even a little easier for us. So we'll choose the principal axes as our coordinate system. Doing that allows us to express our moment of inertia tensor as just elements down the main diagonal and zeros everywhere else, where our I1 is I11, our I2 is I22, and our I3 is I33, in analogy to what we developed earlier. So we can go ahead and evaluate our I dot omega, and also, as far as that matters, our I dot omega dot. So I dotted into omega is just going to become I1, 0, 0, 0, I2, 0, 0, 0, I3. That's 0. Then we're just adding that into omega 1, omega 2, omega 3. Now that just evaluates to I1 omega 1, I2 omega 2, I3 omega 3. And similarly, if we want to do I dot omega dot, that's just going to give us a dot there, dot there, dot there, dot there, dot there, dot there, dot there. All right, easy enough. All right, so we do have to evaluate that omega cross I should make that color other than purple. That's almost impossible to see those dots. There, let's make it orange to make it obvious. So if we're doing I dot omega dot, all these guys just pick up dots. There we go. All right, so now we can go ahead and look at evaluating omega crossed into I dotted into omega. So E1, E2, E3. First row is going to be omega 1, omega 2, omega 3. Last row will be from here, I1, omega 1, I2, omega 2, I3, omega 3. Let's do something different. Let's go ahead and expand the minors just to have fun with that. So we're going to get an E1. So drop, drop, and do those. That's going to give me I3 omega 2 omega 3 minus I2 omega 2 omega 3. Alright, so we'll have minus, but then what I'll do is I'll just flip the minus sign later. So I drop that. Gives me these guys here. So normally this would be a plus, but that's going to be minus. Normally that'd be a minus, but that'll be a plus. So that's going to give me plus E2 times I1 omega 1 omega 3 minus I3 omega 1 omega 3. And then finally do plus E3. So drop, drop, be this minus this, yeah. So that'll be I2 omega 1 omega 2 minus I1 omega 1 omega 2. Alright, for what it's worth, we can clean that up just a shade. We can rewrite that as E1 times I3 minus I2 omega 2 omega 2 omega 3 plus E2 I1 minus I3 omega 1 omega 3 plus E3 times I2 minus I1 omega 1 omega 2. All right. So now we can go back to what we had here before, that n is going to be equal to that. We've figured out both terms, so let's plug it in. So if we write it as a column vector, n1, n2, n3 will be equal to I1 omega 1 dot, I2 omega 2 dot, I3 omega 3 dot, plus omega 2 omega 3 I3 minus I2 omega 3 omega 1 I1 minus I3 omega 1 omega 2 I2 minus I1. Now I permuted these here just because we can go 1, 2, 3, 3, 2, 2, 3, 1, 1, 3, 3, 1, 2, 2, 1 as a way to remember it. If we go ahead and subtract n from both sides, we could rewrite Euler's equation here. In index notation, we could write it as II minus ij omega I, omega j minus sum over k ik omega k dot minus nk epsilon ij k. So this is just an alternate way of writing Euler's equations of motion of rigid bodies. Okay, so let's revisit our friend, the rotating rigid dumbbell, as an example here. So got two point masses like so, connected with a massless rod. So we'll say it's M1, that's M2. We'll go ahead and say that these are going in some sort of nice little circular orbit like so. Same with that guy down there. So this is going to give us, oops, this is going to give us omega pointing straight up. Now, we know that we've already seen before that that is not how the angular momentum is going to point. Let's go ahead and just use the middle of the rod as our axis here. That would be an R1 here, and likewise that would be an R2 there. And since we're choosing the middle of the rod, we'll say that R1 equals R2 equals B for the length. But if we go and look at this, we can see that velocity has to be tangent, that velocity has to be tangent, so the momentum here is going into the page. You go ahead and do the right-hand rule on this guy and that guy. You should be able to convince yourself that the angular momentum points off axis. We've seen that before. All right, so let's go and extend this down just so we can define it. So we'll say that when we're erecting our coordinate system, probably what will make it most sense to do is we'll go ahead and run with the obvious symmetry center and choose this to be my E3 direction. Now let's go a little thicker, make it easier to see. So we'll say that's my E3 direction like so. The angular momentum would be a good choice for my E2. And then as a result, E1 is going to be, let's see, pointing into the screen right there. I'm not going to bother drawing it because it's going to get too cluttered. All right, so let's say the angle that omega makes with the E3 axis is alpha. Okay, so I think we got everybody all set aside here. All right, so we can go ahead and write our angular momentum. That's going to be sum over the particles, m alpha, r alpha, crossed with the appropriate v alpha. And that's just going to be equal to the 2 component of the angular momentum in the x2 direction, because that's how we set it up. All right. That's going to come at the cost of conveniently writing my omega. So omega is going to be equal to E2 times omega times sine alpha plus E3 omega cos alpha. All right. Moments of inertia. We can see here for both the 2 and the 1 axis that I1 will equal I2 will equal M1 plus M2 B squared. And then I3 going along this way is equal to 0. All right. So we can go ahead and calculate our angular momentum. That's going to be I dotted into omega. So that's going to be 1, 1, 0, and then zeros everywhere else, times m1 plus m2 b squared. Matrix product with 0 sine alpha cosine alpha times omega. All right, so we can pull out all the scalars. M1 plus M2 b squared omega 1 0 0 0 1 0 0 0 0 0 sine alpha cos alpha. Well, okay, there'll be M1 plus M2 b squared omega. Now if we go and take this product through, the only thing we're going to get is 0 sine alpha 0. All right. Now, if we go back and look at this, my omega is fixed. So that means that omega dot is 0. So Euler's equations of motion are n1, n2, and whoa. N1, N2, and 3 will equal 0, 0, 0 plus we've got a omega squared sine alpha cos alpha times 0 minus m1 plus m2 b squared 0, 0. All right. So the torque that we have to exert on this dumbbell in order to keep the angular velocity vector pointing in a constant direction rather than the angular momentum, is just going to be E1 times a minus m1 plus m2 b squared omega squared sine alpha cosine alpha. You can clean that up a bit with some half angle, double angle relations, but life's short. All right, now there's something else to notice when you're looking at the Euler equations. If we go back here for a moment, you can see that they only depend on the I1, I2, and I3. So they just depend on the principal moment, on the moments of inertia. So we need to think what the simplest possible body, so to help visualize, we can think about what the simplest possible body would be of 3 distinct principal moments, and that's an ellipsoid. So we can talk about any object and converting it into what we call the equivalent ellipsoid. And that can help us think about it. And all the motion can be modeled as the motion of this equivalent ellipsoid as long as we don't have any dissipative forces. Okay, more on some of that in the next video where we go and analyze a free rotation.